Have you ever stopped to think about the absolute magic that's packed inside your smartphone? You know, the instant communication, the pinpoint location, all of it? We totally take it for granted, right? But its origins, well, they're anything but ordinary. Okay, let's get into this, because the device in your pocket tells a pretty incredible story. A story that was actually born from a global struggle for survival.
So just imagine this for a second. A teenager in Seoul pulling out their phone to find the quickest way to a coffee shop. Super normal, something we see or do every single day.
And then picture this. Halfway across the world, a farmer in Iowa is checking on his crops, specifically the soil moisture, using a satellite link. Again, just modern tech making a really complex job seem almost effortless.
Now, on the surface, those two things have absolutely nothing to do with each other, but they share a common ancestor, a technological root that is deeply surprising. So what on earth is the connection?
Here it is. It sounds kind of wild, but both of those things are, in fact, peace dividends of the Cold War. You see, the foundational technologies that make our digital world possible weren't dreamt up for us, for consumers. Nope, they were forged in the fire of a high-stakes existential arms race between the United States and the Soviet Union.
To really get how this happened, we've got to start with a very specific and very serious problem. It was a strategic crisis that the U.S. Air Force gave a pretty dramatic name: the tyranny of numbers.
The idea behind it is actually pretty simple, but it's also terrifying. When you keep adding more and more individual parts to a complex machine, say a missile, the chance that just one of those parts will fail gets closer and closer to 100%. The system becomes so complex that it's basically guaranteed to break down.
And we are talking about an insane level of complexity here. Back in the 1950s, an intercontinental ballistic missile, an ICBM, could have a guidance system with as many as 100,000 separate hand-soldered parts. Think about that. Transistors, resistors, capacitors, all put together by hand. So here's the kicker. Even if every single one of those parts was 99.9% reliable, which, by the way, is really, really good, the chances of all 100,000 of them working perfectly at the same time were practically zero. For the Air Force, this wasn't just a tech headache, it was a massive strategic vulnerability. I mean, your nuclear deterrent is pretty useless if it can't even get off the launch pad.
So how in the world do you beat something like the tyranny of numbers? Well, the solution turned up, and it was the integrated circuit. But this brand new technology wasn't first picked up by the consumer market. No way. It was adopted by the military. This is the story of how the missile literally bought the chip.
Get this. Back in 1962, the commercial market for these newfangled integrated circuits was zero. A big fat zero. They were way too expensive, they were slow, and nobody had proven they actually worked. The entire market, 100% of it, was the Department of Defense.
So, the Air Force did something pretty radical for its Minuteman II missile program. Instead of using a clunky, heavy, unreliable computer built with tons of separate parts, they paid for a new one built with these integrated circuits. The result? It was 50% lighter, which meant the missile could fly farther, and it was way, way more reliable. Just like that, the tyranny of numbers was defeated.
The Air Force basically became the industry's first, last, and only customer, and that single decision changed everything. The huge number of chips the military bought drove the price of a single chip down from a jaw-dropping $50 in 1962 to just a little over $2 by 1968. That's a price drop almost entirely subsidized by the American taxpayer for national security that ended up making all consumer electronics possible down the line.
And this huge initial investment just kicked off a snowball effect. Once the military proved the tech worked and forced the price down, other government agencies could grab the baton and push it even further.
So while the Air Force was driving up the volume, NASA's Apollo program was driving up the complexity. The computer on board the Apollo spacecraft had to work perfectly for weeks in deep space with zero chance of a repair. To pull that off, the engineers used thousands of simple, identical chips, 4,100 of them to be exact. Their logic was that it was safer to perfect one simple component than to design lots of complex ones. This project also pioneered the idea of fault-tolerant computing, using a dedicated backup computer, a philosophy that's totally standard in critical systems today.
But the government's influence didn't stop there. By the late 70s, the new problem wasn't making chips, it was designing them. So DARPA, the Pentagon's Wild Ideas Research Agency, stepped in. They funded programs to separate chip design from manufacturing, they funded a service called MOSIS that let university students prototype chips for cheap, and they directly funded research at Berkeley and Stanford that led to the RISC processor. And you know what those university projects turned into? The companies that kickstarted the whole workstation boom. Sun Microsystems, Silicon Graphics. You can draw a straight line from a military problem right to the birth of Silicon Valley.
But if you want the final undeniable proof of just how successful this model was, you have to compare it to the competition. Because this wasn't just an arms race of warheads, it was an asymmetric race in technology and economics.
And wow, the contrast is stark. The US used what they called a merchant model. They funded a bunch of competing private companies like Fairchild and Texas Instruments and let them battle it out. The Soviet Union, they used a top-down state-controlled system. So while American missiles were getting these sophisticated integrated circuits, Soviet systems were often still stuck using older, less reliable tech like miniaturized vacuum tubes. The American way created this dynamic, thriving commercial ecosystem, while the Soviet way, well, it led to a pretty significant tech lag. And this wasn't just a guess. Intelligence reports from the time confirmed it. A CIA assessment concluded that if the Soviets ever got their hands on American semiconductor technology, it would have massively sped up their own programs they were really struggling to get off the ground on their own. The gap was real, and it was a big deal strategically. So at the end of the day, the crucial point is that this technological lead, which was born from this really unique model of military investment, had huge, world-changing consequences. Ultimately, the Cold War wasn't won by launching missiles. It was won by building the kind of resilient, innovative economy that this technology unleashed.
You know, when you think about where the internet came from, what's the first story that pops into your head? For most of us, it's this really dramatic tale of Cold War survival. Right? The legend is that the internet's forerunner, the ARPANET, was built to be basically indestructible. A communications system tough enough to withstand a full-on nuclear attack so the government could retaliate from the rubble. It's an awesome story, almost like something out of a movie.
But is it actually true? Was the network that grew into our modern internet really born from the fear of atomic annihilation? Well, as it turns out, the reality is a way more fascinating tale of two completely different problems that just happened to find a single revolutionary solution.
So let's start with the first thread of the story, which, to be fair, absolutely begins with the Cold War. We're talking the early 1960s, and military strategists at the Rand Corporation were staring down this terrifying possibility: nuclear decapitation. And this slide just lays out the problem perfectly. On the left, you've got the system they had, which was basically modeled on the AT&T phone network, super centralized. A few key switching centers handle everything. Now, if a Soviet missile takes out those hubs, poof, the entire command structure is silenced. So this researcher named Paul Baran comes up with a radical idea you see on the right: a distributed fishnet-style network, no central authority. You could vaporize a few nodes, and communications would just find a new path around the damage. So how in the world do you make a fishnet network like that actually work? Well, Baran's brilliant invention was something called packet switching. The whole idea was to chop up any message, any piece of data, into these tiny, uniform pieces or packets, and each packet would be sent out into the network to find its own way to the destination. It's kind of like a crowd of people all trying to get to the same place, but they all take different streets to get there. And this pretty much sums up Baran's whole vision. His goal was 100% nuclear survivability. His method involved what he playfully called hot potato routing. Each node would just grab a packet and pass it along as fast as it possibly could. But here's the crucial point. While the idea was born, it was purely theoretical. AT&T thought it was impractical, and the Air Force never actually built it. So it was this amazing solution for a military problem that, at the time, went absolutely nowhere. Okay, so let's put a pin in that military story for a second. Because at the exact same time, a completely different government agency, ARPA, was dealing with a totally different kind of problem. A problem of economics, not extinction. You see, ARPA was pouring tons of money into cutting-edge computer research at universities all over the country. But there was this huge issue. A computer at MIT couldn't talk to a computer at UCLA. They were like these expensive, isolated islands. And that meant if one research team developed some amazing software, another team across the country had to basically buy a whole new, identical computer just to run it. It was just incredibly wasteful.
So ARPA's whole goal for building a network, the network that would become the ARPANET, was simple: resource sharing. It was an economic efficiency measure, pure and simple. They just wanted a researcher in Utah to be able to log in and use a unique computer in Massachusetts. This network was not designed to survive a bomb. It was designed to share really, really expensive calculators.
Okay, so we have two totally separate stories running in parallel. One is about surviving nuclear war, and the other is about saving money on mainframe computers. And this is where they finally and famously converge.
This slide right here is the key to the entire story. Just look at the top two rows. The problem and the goal for Boron and for ARPANET are completely different worlds. But then look at that bottom row. The technology they both needed was the exact same thing: packet switching. The ARPANET team adopted packet switching not because it was resilient, but because it was the most efficient way to send computer data. And that's how the myth was born. The technology designed for nuclear war got used to solve an economic problem.
And this leads to a pretty fascinating outcome. Even though the reason for building ARPANET was all about sharing resources, it inherited the DNA of Barron's military concept. The incredible robustness of today's internet, the way it can route around a severed cable or a massive server outage, that is a direct genetic inheritance from that original Cold War paranoia. It got its toughness for free.
But the story doesn't quite end there, because the ARPANET wasn't yet the internet that we know today. For that to happen, the entire network had to be totally reborn in a single, really dramatic day. So the early ARPANET ran on a protocol called NCP, and it worked fine for a single network, but it was clunky. It couldn't really handle connecting different types of networks together, like satellite networks or radio networks. But more importantly, it had a hard-coded physical limit to its growth. It was hitting a wall.
And that limit was just 256 hosts. That's it, 256 computers. I mean, it seems absolutely absurd today when billions of devices are connected, but that 8-bit address scheme was a concrete ceiling that the network was about to slam into.
So a new, much more flexible protocol was designed, TCP/IP, the language of the modern internet. But how do you get everybody to switch over at once? Well, the military made a command decision. They declared January 1st, 1983 as Flag Day. It was a mandatory all-at-once switchover. Every single machine on the entire network had to flip to TCP/IP on that specific day, or they would be cut off forever.
This simple timeline really clarifies the two key moments here. In 1969, you have the ARPANET, the resource-sharing network, first going online. But a lot of people argue that January 1st, 1983, Flag Day, is the true birthday of the internet. It's the moment it got the universal language it needed to grow into a global network of networks.
And this is why this whole thing matters so much. This switch was a massive feat of coordination that was only possible because of military authority, or fiat. In a commercial world, with all these competing companies, trying to get everyone to agree to adopt a single standard on a single day, it would be basically impossible. This top-down decision created the universal standard that allowed the internet to scale into what it is today.
So the internet wasn't actually born to survive a nuclear war, but its incredible resilience is a direct result of that fear. And its global scale was made possible by a kind of top-down command decision that we rarely ever see anymore.
We always talk about the internet being the nervous system of our world, connecting everything. But if that's true, then GPS, the Global Positioning System, is its vestibular system. It's that invisible, silent sense that gives our entire world its balance and its sense of direction. I mean, think about it. It gets you where you're going, it finds you a date, it orders your lunch, it even keeps the whole global financial market in sync. It's as basic as electricity now, but it's totally invisible. Just a bunch of satellites way up there constantly whispering what time it is. So where did this magic trick come from? It didn't just fall out of the sky. It's this wild story full of Cold War drama, some seriously brilliant physics, and one single decision that basically changed everything overnight. So let's rewind. All right, so the story of GPS doesn't start with a friendly voice telling you to turn left in 500 feet. Nope. It starts with maybe the most terrifying problem of the 20th century. Imagine you're in a nuclear submarine deep under the ocean. How do you know exactly where you are so you can launch a missile and hit a tiny target halfway across the planet? It literally all started with a beep, beep, beep. When the Soviets launched Sputnik in 1957, some scientists realized they could track it by listening to the Doppler shift in its radio signal. Like how an ambulance siren changes pitch as it drives past you. And that's when they had this genius idea. Wait a minute, if we can find the satellite by listening to its signal, what if we flip that around? If we know exactly where the satellite is, can we use its signal to find out where we are? And that was the aha moment the Navy was desperate for. So they built this first system. They called it Transit. And look, it was a start, but it was so slow. I mean, a sub would have to wait for hours just for a satellite to pass overhead to get one little 2D ping on the map. For a fighter jet or a missile, totally useless. They needed something that worked everywhere, all the time, in 3D, and right now. So they realized they were looking at the problem all wrong. It wasn't really about your position in space. To solve that, they first had to solve for something way more fundamental. They had to solve for time. The whole thing became a race against the clock. Now, the basic principle here is actually pretty simple. It's called trilateration. All it means is that if you know your exact distance from 3 different points, in this case 3 satellites, there's only one possible spot on Earth you can be. It's just geometry. And the physics seems easy too. A satellite just beams down a signal that's stamped with the exact time it was sent. Your phone gets it and checks its own clock. That tiny little delay is the travel time. And since that signal travels at the speed of light, you just do the math. Speed times time equals distance. Simple, right? But the whole thing, that entire beautiful equation, completely falls apart if your measurement of time is even a tiny bit off. And when I say a tiny bit, I mean impossibly, mind-bogglingly tiny. To know your position within about 10 meters, the clocks across the whole system have to be synced up to within 30 times nanoseconds. That's 30 billionths of a second. Just to put that in perspective, if your clock was off by just 1,000th of a second, your GPS would think you're almost 200 miles away from where you're actually standing. It's just an insane level of precision. So yeah, that little quartz clock in your watch or your phone, not gonna cut it, not even close. So they had to do something that sounded completely crazy back then. They had to launch atomic clocks, these huge, hyper-accurate but incredibly delicate lab instruments, on top of rockets and shoot them into space. People thought they were nuts. Could these fragile things even survive the launch, let alone the radiation? Well, a program called Constellations proved that amazingly, they could. Okay, great. Problem solved, right? We have perfect clocks in orbit. But wait, that just creates a new massive problem. Atomic clocks are expensive and big. You can't put one in your pocket. So how on earth do you make a system for everybody if they all need a perfect clock? How do you basically give everyone on the planet an atomic clock for free? This was the real barrier. The system needs perfect time, but the gadgets we all use have to have cheap, kind of sloppy clocks in them. It's a complete contradiction. And frankly, it's the one thing that could have kept GPS locked away as a military-only toy forever. So that was the million-dollar question. How do you make a $5 clock in your phone act like a $100,000 clock on a satellite? You can't just build a better one. But maybe, just maybe, you could fix it with math. And the solution they came up with, oh, it's just so clever. It's beautiful. The answer wasn't a better clock. It was just one more satellite. Okay, so check out this hack. With 3 satellites, you can solve for 3 unknowns: your X, Y, and Z coordinates: latitude, longitude, altitude. But the cheap clock in your phone creates a 4th unknown, that little bit of time error. Well, in algebra, if you have 4 unknowns, you need 4 equations to solve it. And that is what the 4th satellite is for. It gives you that 4th measurement you need to solve for T, the time error. It lets your phone figure out exactly how wrong its own clock is, and then it just corrects for it on the fly. It's a pure math trick. It's absolutely brilliant. Now, of course, the US wasn't the only country playing this game. The Soviet Union was building its own system, GLONASS. And it was actually really smart. They tilted its orbit to work better over the high latitudes in Russia. But then the Soviet Union collapsed, the funding dried up, and the system just started to fall apart. It's a powerful reminder that this kind of amazing tech doesn't just run on science. It needs constant money and political will to survive. So the technology is there. It works, the science is solid, but that's not the end of the story. The final piece of the puzzle isn't technical at all. It's political. It's the story of how this top-secret weapon was basically given away to the entire world. And the turning point was a terrible tragedy. In 1983, a Korean air passenger jet got lost because of a navigation error, straight into Soviet airspace, and was shot down. So President Reagan promised that to prevent that from ever happening again, the US would let civilians use GPS. But the military was still nervous, so they intentionally messed up the signal for everyone else. It was called selective availability, and it meant your GPS was only accurate to about 100 meters. And that's how it was until May 1st, 2000. On that day, President Clinton ordered selective availability to be turned off for good. And look at this. Overnight, just like that, the accuracy for every person on the planet got 10 times better.
You went from knowing you were somewhere on a football field to knowing exactly which room you were in.
And the result of that one decision? Well, this is what happened. Suddenly, companies could build real products with this technology. Demand exploded, and as they started making millions of GPS chips, the price just plummeted from thousands of dollars down to about $1.50. The floodgates were officially open.
And you really have to let this sink in. That one political decision is the direct ancestor of our modern world. Without it, there's no Google Maps, no Uber, no Tinder, no Pokemon Go. All these massive industries, all these things we just take for granted every day, they were all born in the moment that switch was flipped.
Think about it. You're at a concert, maybe a football game, you're surrounded by tens of thousands of other people, and somehow your call connects, your photo uploads. This isn't just a neat feature. It's the solution to a massive technical problem. How does your one tiny signal cut through all that digital chaos?
I know, that sounds completely random, right? A Hollywood actress and torpedoes. But that's exactly where this incredible story kicks off. The tech that lets you post a selfie from the nosebleed seats was born during World War II, thanks to some very unlikely inventors.
And this brings us to one of the most improbable collaborations you could possibly imagine. This wasn't a team of engineers in lab coats. Nope. This was a partnership born from Hollywood glamour and, of all things, experimental music.
So on one side you have Hedy Lamarr, who was one of the biggest movie stars on the planet in the 1940s. And on the other side, George Antheil, a composer famous for his wild, experimental, and frankly chaotic music. What on earth could these two possibly have in common? Well, it was a shared passion to defeat the Nazis. See, they knew radio-controlled torpedoes could be a huge advantage, but there was one massive flaw. If the enemy found the guidance frequency, they could just blast it with static, jamming the signal and sending the torpedo way off course. Lamarr and Antheil wanted to make that signal completely jam-proof.
Their incredible idea was something called frequency hopping, and the concept is just genius in its simplicity. Instead of sending a signal on one single easy-to-find channel, what if you made it jump around between frequencies so fast that no one could ever lock onto it?
Now, here's the really cool part. Their model for this was a player piano. Just picture it, 2 synchronized piano rolls, one on the ship and one inside the torpedo. As the rolls turn, they trigger the radio signal to hop between 88 different frequencies. Yep, the same number of keys on a piano. Only the sender and receiver know the secret tune of the hops.
And this right here is the beauty of it. To anyone else trying to listen in or jam the signal, it wouldn't sound like anything. It would just be random static, total gibberish. The message was essentially hidden in plain sight. But, like so many revolutionary ideas, this one was way, way ahead of its time. Its journey from a patent on a piece of paper to something you could actually use was going to be a long one.
And you can kind of see their point, right? The idea of trying to stuff a complicated mechanical player piano into a torpedo that's about to be fired into the ocean, well, the Navy just thought it was too bulky, too impractical. They rejected it, the patent eventually expired, and the whole idea was basically shelved.
But a great idea doesn't just die. It just waits for the technology to catch up. And it did. A couple of decades later, in the 50s, engineers could finally ditch the clunky piano rolls and use tiny, solid-state transistors. And by 1962, at the absolute height of the Cold War, U.S. Navy ships blockading Cuba were using this exact tech to send secure messages that Soviet intelligence couldn't track. Hedy Lamarr's idea had finally found its moment.
Okay, so just when you think you've got this story figured out, it takes another wild turn. We're leaving the Cold War oceans behind and heading out into the vast emptiness of space, where a completely different kind of problem needed a solution.
Think about the Voyager probes. They're sending back these priceless pictures and data from Jupiter or Saturn and beyond, but by the time their signals travel billions of miles to reach us, they are unbelievably faint. We're talking about a whisper in a hurricane of cosmic noise. So how in the world do you pull a clear message out of all that static?
The answer came from a professor named Andrew Viterbi. He created this incredibly elegant algorithm that could analyze a garbled, noisy signal and make a statistically brilliant guess about what the original message most likely was. It was a revolutionary form of error correction, and it's how NASA was able to piece together those iconic images from the outer solar system.
So now we have these two amazing but totally separate ideas. A military trick for hiding signals, and a deep space algorithm for cleaning them up. So what happens when you decide to smash them together?
Well, you get the modern cellular revolution.
Okay, fast forward to the 1980s. Cell phone networks are starting to get really crowded. And Andrew Viterbi, who now has his own company called Qualcomm, comes along with this radical pitch. He says, hey, you know that spread spectrum idea the military uses, the direct descendant of Hedy Lamar's frequency hopping? What if we combine that with my error-correcting algorithm to fix cell phones?
Now, to get just how big a deal this was, you gotta look at the old methods. The first one, FDMA, was like giving every single person their own private radio station. It worked, but you ran out of stations fast. Then came TDMA, which was more like giving everyone the same channel, but making them take turns talking. Better, but still limited. Viterbi's idea, CDMA, was something else entirely. It was like letting everyone talk at the exact same time, in the same room, but each person is speaking a different language.
And this is the absolute magic of it. Every single phone call gets its own unique digital code, its own language. Your phone's receiver knows your code, so it listens to this huge jumble of conversations happening all at once. Then, and this is the key, it uses the power of the Viterbi algorithm to filter out all the other languages and perfectly reconstruct just your conversation. It's brilliant.
This combination of a WW2 secret and a deep space formula was a total game changer. It massively increased how many people could use a cell network at once, and it became the foundational technology for 3G, which is what really gave us the mobile internet that we can't live without today.
So, when you pull your phone out of your pocket, you're not just holding a piece of cool electronics, you're holding a piece of history. You're holding this incredible, invisible legacy.
What an absolutely wild journey, right? An idea that started with a Hollywood star trying to sink enemy ships became a vital tool for Cold War communication, got refined to hear the whispers of other planets, and finally, it was perfected to solve the problem of everyone wanting to make a phone call from the same stadium.
It just goes to show you that the biggest innovations often come from the most unexpected places. They happen when people combine ideas from completely different worlds, from avant-garde music to space exploration, to create something nobody had ever thought of before.
How does your phone know to rotate the screen when you turn it sideways? Or, how does a racing game know you're tilting it to steer? It feels totally seamless, almost like magic. But, well, the origin of this magic is anything but simple.
And believe it or not, the tech that lets you watch a video in landscape mode, it's a direct descendant of the hardware designed to guide nuclear weapons. Yeah. To understand how on earth that happened, we need to jump back in time a bit.
All right, so our story kicks off with a massive life-or-death problem from the Cold War. How do you guide a missile to hit a tiny target thousands of miles away with no GPS to help you out? The answer was a little device called an accelerometer.
I mean, just look at this transformation. It's absolutely wild. What started out as this piece of military hardware about the size of a soup can and costing thousands of dollars is now a microscopic little silicon chip that costs pennies. That journey from a missile silo into your pocket is exactly what we're about to unpack.
So the technology that made all this possible is called MEMS. That stands for Micro Electromechanical Systems. Just think of them as these tiny microscopic machines with actual moving parts, like little beams and gears, all built right onto a silicon chip, just like a computer processor. It's miniature engineering taken to a whole other level.
And the original mission for these things? It was as high stakes as it gets. These early accelerometers were the absolute heart of the guidance systems for the Titan II missile and even the Apollo spacecraft. The precision here was critical. We're talking about the difference between a nuclear warhead hitting a fortified military silo versus missing and hitting a city full of civilians.
So how did this super serious military tech end up in your phone? Well, after the military, through agencies like DARPA, helped shrink it down, the technology found a really unexpected new home. The real game changer, the moment that put this tech on the path for all of us, wasn't another weapon or a phone. It was the car.
This right here, this was the tipping point. In the 1990s, the auto industry figured out that these super precise little accelerometers were perfect for reliably deploying airbags in a crash. This created a huge new market, forcing manufacturers to pump them out by the millions, which, of course, sent the cost just plummeting. And all of a sudden, this once exclusive military tech was cheap enough for literally anyone to use.
But that motion sensing stuff, that's only half the story. The other key piece of Cold War tech that's sitting in your phone isn't about moving at all. It's about listening. Specifically, it's about finding one tiny, critical signal in an absolute ocean of noise.
Okay, so check this out. The term DSP has this fascinating double life. During the Cold War, DSP stood for the Defense Support Program, which was this network of spy satellites constantly watching for the heat signature of a Soviet missile launch. But today, DSP means digital signal processing, the chips that make our entire digital multimedia world possible. And as you're about to see, these two things are deeply, deeply connected.
You have to imagine, the military was just drowning in data. They had information pouring in from all these satellites, and from these huge networks of underwater microphones, called hydrophones, that were just listening for enemy submarines. The challenge was, how do you process all of this data in real time to find the one sound or the one image that actually matters?
Just think about how incredibly hard this is. The goal was to find a distinct Soviet submarine propeller sound in a noisy ocean. That monumental needle-in-a-haystack task is precisely what digital signal processing was invented to solve.
It's truly incredible when you realize it's the exact same mathematical architecture doing the work today. The process of finding a submarine's unique sound in a noisy ocean is fundamentally the same math that's used to decode an MP3 for your headphones. The algorithms they use to sharpen a fuzzy spy satellite photo are the same ones that process the JPEGs on your phone. It's all just filtering a signal.
Okay, so now we have our two threads, missile guidance and spy satellites. Let's start weaving them together and see the whole picture.
So, there you have it. This is your phone's hidden family tree. One branch starts with nuclear missiles and ends with you tilting your screen to play a game. The other branch starts with spy satellites hunting for submarines and ends with you listening to music or snapping a photo. Two totally separate streams of Cold War innovation, and they both converge right into the device in your pocket.
When you put it all together, the conclusion is just inescapable. The smartphone, this thing we see as a tool for connection and entertainment and modern life, it's built directly on a foundation of technologies that were first dreamed up and paid for the sole purpose of global conflict. Okay, so let's trace the family tree of your digital assistant. You're about to see how a classic battlefield problem, way too much information and not nearly enough time to sort through it, led directly to the AI that lives in your pocket.
It all kicks off back in 2003 with DARPA. If you don't know DARPA, they're basically the Pentagon's what-if department, the agency for absolute moonshot projects. They launched this program called PAL, which stood for Perceptive Assistant That Learns, and the whole goal was to solve a massive issue, cognitive overload. Commanders on the ground were just drowning in data from drones, satellites, troops, you name it. They desperately needed a smart assistant to help them cut through all that noise.
Now, the main event under this PAL program was called CALO, the Cognitive Assistant That Learns and Organizes. And listen, this was not some small side project. The scale here was immense. We're talking a massive multi-university effort with over 300 of the brightest researchers, all laser-focused on one thing, creating an AI that could actually understand plain English and help a commander manage everything from complex battlefield data to just, scheduling their daily meetings.
And this timeline just lays it all out perfectly. You can literally watch the journey from a top-secret military lab straight into your pocket. See, the technology was just too good to stay locked up in the world of defense. So in 2007, the Lead Research Institute spun it off into a commercial startup you might have heard of, Siri Incorporated. And the transition to the consumer world? It happened in the blink of an eye. Just 3 years later, boom, Apple buys them up. And by 2011, this Pentagon-funded AI assistant was a core feature of the iPhone 4S.
So that's Siri. But it's not the only piece of your phone's secret history. Next up, let's talk about another piece of futuristic tech we're all fascinated by, self-driving cars. And their story doesn't start in some pristine, clean lab. Nope. It begins with a spectacular, almost comical failure, right in the middle of the Mojave Desert.
You have to understand, the motivation here was incredibly urgent and serious. In the early 2000s, U.S. forces in Iraq and Afghanistan were facing just devastating losses from things like IEDs and ambushes. So to save lives, Congress passed a mandate. They said that by 2015, 1/3 of all ground combat vehicles had to be unmanned.
So to make this happen, DARPA did what DARPA does. They created a competition, the Grand Challenge. They offered a $1 million prize to any team that could build a car to drive itself across 142 grueling miles of desert. The very first race, back in 2004, was an absolute disaster. Not a single vehicle finished. The best one, the star of the show, made it a whopping 7.5 miles before it just gave up. The problem was clearly way, way harder than anyone imagined.
But here's the thing about DARPA. They don't give up. They double down.
They doubled the prize money to $2 million and ran the whole thing again just 1 year later. And the result? It was incredible. A stunning success. 5 vehicles completed the entire brutal course. That initial failure had completely lit a fire under the entire research community.
And the legacy of that desert race is so incredibly direct, it's almost hard to believe. The leaders of the winning teams from Stanford and Carnegie Mellon, they were immediately snapped up by Google to create its self-driving car project, which we now know as Waymo. The core algorithms they developed, the very brains that were supposed to keep military-supplied trucks safe, became the foundation of the entire multi-billion-dollar autonomous vehicle industry.
So you're probably seeing a pattern here, right? Siri and self-driving cars, these aren't just isolated examples. They're actually part of a much bigger, kind of paradoxical story that goes all the way back to the Cold War, a time when preparing for global annihilation accidentally created the foundations of our modern, connected world.
I mean, just think about the kind of problems they were trying to solve back then. You needed missiles with their own little brains to find a target halfway across the world. You needed communication networks that could still work even after a nuclear strike. You needed radios that absolutely could not be jammed by the enemy. These military must-haves forced the invention of technologies that became the literal building blocks of everything from the internet to GPS.
The pattern is just crystal clear when you look at it like this. That tiny, powerful computer inside a Minuteman nuclear missile, it became the microprocessor inside your laptop. The Navy's super-duper accurate clocks they needed for submarines, that became the GPS that powers your Uber and gets your food delivered. The secret codes developed for guiding torpedoes, they laid the groundwork for our 5G networks. Time and time again, technologies built for war were repurposed for peace and for commerce. So, what's the big takeaway from all this? Well, it really forces us to rethink where true, fundamental innovation comes from. It asks us to see the government not as some kind of barrier, but as an unlikely and maybe even essential engine for progress.
This history suggests a completely different model for innovation, one you could call the state as a risk absorber. I mean, it flies in the face of the idea that government just gets in the way. Instead, it shows the government tackling the huge, wildly expensive, long-term problems that, frankly, no private company in its right mind could afford to take on. They absorb all that initial risk, creating the foundation that the private sector can then build on and commercialize later.
Which, of course, brings us right back to your phone. It's so easy to look at it and just see this sleek, beautiful product from a design studio in California. But when you really understand its history, you realize it's something so much more. It's a pocket-sized museum of the Cold War, a whole collection of technologies born from conflict, repurposed from swords into digital plowshares.
Have you ever stopped to think about how a live video call can just bounce from New York to Tokyo in like an instant? Or how your car's GPS knows exactly where you are right now? Believe it or not, our story starts not in some high-tech lab, but in the imagination of the science fiction legend Arthur C. Clarke. We're talking way back in 1945. He used what he'd learned about radar during the war and published this idea that sounded completely out there. A network of just 3 satellites positioned perfectly in space that could cover the entire planet with communication signals.
Now, the really cool thing is, Clarke's idea wasn't just fantasy. It was based on solid science. He figured out that at this very specific altitude, a satellite would orbit at the exact same speed the Earth spins. So for us down here on the ground, it would look like it's just hanging there, motionless in the sky. I mean, what a perfect, fixed point to bounce signals off of to anywhere in the world. It was a brilliant theory.
But that's all it was back then, a theory. In 1945, the kind of rockets and electronics you'd need to actually do this, well, they just didn't exist. Clarke's vision was basically a dream, just sitting on a shelf waiting for some kind of push, a catalyst powerful enough to turn science fiction into cold, hard fact.
And that catalyst? It turned out to be the incredibly intense, high-stakes rivalry between the United States and the Soviet Union. All of a sudden, Clarke's concept wasn't just a neat idea for, say, global television anymore. No, it became a matter of national survival. It was a strategic imperative that was about to kick off a massive technological revolution.
And this is the moment that changes absolutely everything. The era of just thinking about it, the theoretical era, it comes to this sudden screeching halt, and it's replaced by a whole new age of anxiety and ambition. The space race was officially on.
Just look at this timeline for a second. You see that long pause? 12 years of pretty much nothing after Clarke published his idea. Then 1957 hits, and bam, you see this rapid-fire explosion of innovation get unleashed. So what on earth happened in 1957?
On that day, the Soviet Union launched Sputnik 1. For the very first time, a man-made object was circling the Earth, and its little radio signal beeping as it passed over the United States was a massive psychological blow. The oceans that had protected America for centuries, suddenly they felt completely meaningless.
The satellite itself was, honestly, incredibly simple. It was just a polished metal ball that transmitted this repetitive beep, but its message, that was loud and clear. If the Soviets could put this little sphere into orbit, it meant they had the rocket power to deliver a nuclear warhead to any city in the United States. So yeah, the critical thing wasn't really the satellite. It was the massive rocket that got it up there.
The American response was, as you can imagine, immediate and huge. The shock of Sputnik kicked off this frantic technological race, not just to get into space, but to control it for communication.
And this slide just perfectly shows that rapid-fire progress. In just 1 year, the U.S. launched Project SCORE, which broadcast President Eisenhower's voice from orbit. Then came Project Echo, basically a giant metallic balloon acting like a mirror for radio waves. Pretty clever. That was followed by Courier 1B, an active satellite that could actually store and forward messages, a direct precursor to email. By 1962, we had Telstar transmitting live TV across the Atlantic. And then, finally, in 1964, SYNCOM-3 actually achieved Clark's original vision, a true geostationary orbit, beaming the Tokyo Olympics live to the U.S. Incredible.
So with the technology now proven, the US found itself facing a totally new kind of problem. This one wasn't about physics, it was about policy. Now that this powerful new domain was open for business, who was going to control it?
I mean, think about it. Should it be a government monopoly, like the Postal Service? Or should it be handed over to a private communications giant like AT&T? The answer to this was going to define the future of how information flows around the globe.
So here was the core issue. A lot of people in Congress were really worried that giving one company, like AT&T, total control over space communications would create this massive, unchallengeable monopoly. So the solution was a really clever compromise, a brand new law that created a unique kind of entity, a private corporation that would operate under federal regulation.
JFK signed this thing into law, and it created ComSat, the Communications Satellite Corporation. But it did something else, something really important. It mandated that this new technology had to serve global needs, and that included less developed nations. This single act laid the foundation for Intelsat, the international group that would go on to manage the global satellite network.
Okay, so the ultimate result of this new policy was this fascinating split. It basically created two parallel universes for space communication, and each one had a very, very different mission.
So on one side, you had the civilian track, which was led by ComSat and Intelsat. Their goal was all about commerce, connecting the world with telephone calls and TV broadcasts. But on the other side, you had this totally separate, super secure military track, focused entirely on national security, making sure that a command and control network could survive pretty much any kind of attack.
And this dual system, one for public business and one for national security, that's the architecture we all inherited. It's the very foundation of that invisible mesh of data that surrounds us every single day. And it was all born from this mix of science fiction, Cold War terror, and some really forward-thinking policy.
All right, let's dive into a really fascinating, kind of hidden story. It's about a secret line that connects the terrifying brink of nuclear war directly to the wallet in your pocket.
I mean, it sounds like a weird riddle, right? How could a nuclear bomb possibly have anything to do with your secure bank transfer? Well, the answer, as you're about to see, is buried in the secret infrastructure that was built completely in the shadows of the Cold War.
So to get this, we got to go back in time, right to the height of global tension. This was a time when the biggest fear wasn't just, the devastation of an attack, but the complete and utter silence that would come right after.
Just try to picture it. You've got strategic forces, command centers, the entire chain of command, and they're all cut off from each other at the most critical moment in human history. A single high-altitude nuclear detonation could basically mute an entire continent, severing communications at the exact moment you need them most. That was the absolute nightmare scenario.
And the problem was obvious. The old way of doing things, high-frequency radio, was just way too fragile. It worked by bouncing signals off the ionosphere, which meant it was already vulnerable to stuff like solar flares and atmospheric noise. But the real killer? It would be completely wiped out by a nuclear EMP.
Satellites were the only real way forward, a direct, reliable line of communication flying high above all the chaos and designed from the ground up to survive. So, get this. While the civilian world was all excited about the dawn of the global village with its own satellites, the Department of Defense was busy building a completely separate parallel infrastructure up in space. And it had one single purpose: survival.
This whole secret project really evolved in 3 big stages. It started with some simple first steps back in 1966, then took a huge leap forward in 71, and by 1975, it had become a genuine digital fortress in the sky. The first phase was called the IDCSP, and honestly, by today's standards, these things were incredibly simple. We're talking about little metal spheres just spinning their way through space. They didn't even have thrusters to keep them in one spot, so ground stations had to constantly track where they were drifting. But even with all that, they were revolutionary. For the very first time, the military had reliable, high-capacity links that could carry digital data and voice, which was absolutely critical for operations in the Vietnam War.
But, a simple network just wasn't going to cut it. To survive a full-on nuclear exchange, this thing had to evolve into something way, way tougher. A hardened system that could keep working through the worst conditions you can possibly imagine. It had to become a digital fortress.
So enter the next generation, DSCS-2. This was the quantum leap. Instead of just tumbling through space, these satellites had what's called 3-axis stabilization. That meant they could actually aim their antennas and create these powerful focused beams on specific areas on the ground. This was a game changer. It massively increased privacy and, for the first time, smaller portable ground units could connect to the network. Just a huge advantage.
But all of this cool new tech still had to face the big bad boogeyman of nuclear war, the electromagnetic pulse, or EMP. This is a massive burst of energy from a nuke that can just fry electronics for thousands of miles. To be a real fortress, the system had to be shielded against this one single devastating effect.
And that brings us to DSCS-3, the ultimate digital fortress. This thing was designed from day one to survive, period. Its electronics were hardened against EMPs, and its anti-jamming tech was just incredible. Using these multi-beam antennas, it could literally null out a hostile signal. It could pinpoint an enemy jammer, ignore it, and just keep listening for the friendly chatter.
Okay, so we've got this incredibly tough, secret military network built to survive World War III. So what, right? What does any of that have to do with you? Well, this is where the story comes full circle and lands right in your wallet.
This quote just nails it. Think about it. To make sure your message gets through all the noise and chaos of electronic warfare, you need to be really, really smart about how you send it. So the military invented these incredibly sophisticated error correction codes, and it's those exact codes that are the ancestors of the tech that keeps your digital life secure today.
I mean, you can draw a straight line. The need for jam-resistant communication, that led to secure corporate networks. Those error correction codes, they're why your digital bank transfers are so secure. And even the radiation-hardened electronics, well, they laid the groundwork for the reliability protocols that keep our entire digital world from falling apart. It's a direct technological inheritance.
So let that sink in. Every single time you make a secure purchase online, or you check your bank balance, you are using the ghost of a technology that was forged in the fires of the Cold War. The system built to survive a nuclear apocalypse is now protecting your finances.
All right, let's dive in. We are going back to the 1980s, a time when a brand new technology popped up that didn't just report on world events. It actually started to change them for good.
So here's the big question we're tackling. Could a simple TV camera actually be more powerful than a seasoned diplomat? I know, it sounds a little wild, but by the end of this, you'll see how that's exactly what happened. We're talking about the moment TV news stopped just being a spectator to history and instead started to get right in there and shape it.
And this whole phenomenon has a name, the CNN effect. You know, it really all boils down to one revolutionary piece of tech: the ability to broadcast live video from basically anywhere on the planet at any time, using these new portable satellite uplinks. All of a sudden, diplomacy wasn't just happening in quiet, secret rooms anymore.
Now, there's a fancy academic term for this, teleocracy. But don't let the word scare you. The idea is actually super simple. It just means that global politics started getting pushed and pulled by whatever was happening live on 24-hour news. And yeah, CNN was definitely leading the pack.
Think about the speed of information back then. Before this, you had traditional diplomacy. It was slow, right? Everything had to go through official channels, filtered up through layers of government. But a live broadcast? That's instant. It just completely jumped over all those old systems, and it forced governments to react at the speed of television, not the speed of paperwork.
So when did we first really see this new power in action? Well, for our first big example, we've got to go to Beijing in 1989 to the student protests in Tiananmen Square. All the pieces were there. You had Western news crews from CBS, from CNN on the ground. But the key, the absolute game changer, was that they had these new portable satellite uplinks. So when the government decided to crack down, it wasn't something people just read about in the newspaper the next day. No, they were broadcasting it as it was happening. And that right there, that is the heart of the CNN effect. There was no time lag. Those images of the crackdown were getting beamed straight into people's living rooms all across the world, making this event, thousands of miles away, feel incredibly immediate and personal. And the result? Just this sudden, massive wave of diplomatic pressure. All at once, people were calling for sanctions, for action. These were demands that world leaders just couldn't ignore, because they were seeing the exact same gut-wrenching images as their own citizens. The old quiet way of doing things was just completely steamrolled. Okay, let's jump to our next case study because this is where things really build. Later that same year, over in Berlin, the CNN effect wasn't just creating pressure. It was like pouring gasoline on the fire of historic change. I mean, you had Tom Brokaw from NBC reporting live from the Brandenburg Gate as the Berlin Wall was literally coming down. He said it perfectly. This wasn't just news. It was a shared global experience. People everywhere got to witness the feeling of liberation, live as it happened. And this just kicked off an incredible domino effect. Seeing the wall fall, not reading about it days later, but seeing it live, sent this powerful, undeniable message. If you were a citizen in another Eastern Bloc country, it was instant proof that the old world was crumbling. And that, in turn, helped speed up the collapse of their own governments. Okay, so this all brings us to the climax, really, the moment the CNN effect hit its absolute peak, the first Gulf War in 1991. It literally became known as the First Living Room War. And here's a wild detail. The Iraqi president, Saddam Hussein, he totally got it. He understood this new power so well that even when he was kicking out other journalists, he let CNN keep its special satellite link to Baghdad. He knew the world was going to be watching, and he wanted to have some kind of say in the story. The reporting from that time is just iconic. Hearing Peter Arnett and Bernard Shaw describing the anti-aircraft fire lighting up the night sky, that wasn't like a clean summary on the 6 o'clock news. It was raw, it was unedited, and it was happening right now. It brought the reality of war into people's homes in a way that had never happened before. And here's the part that is so crucial to understand. Because CNN had that exclusive link, the entire world was basically consuming the war as one single, real-time event. It wasn't a bunch of different versions of the story trickling out. It was one live feed. So who was watching? Literally everyone. You had military commanders in the Pentagon, world leaders in their capitals, and the general public sitting at home, all getting their information at the exact same time from the exact same channel. I mean, think about that. That had never ever happened in the history of conflict or diplomacy. So, what's the big takeaway from all this? What's the lasting legacy? Well, it was way more than just a cool new technology. It was a permanent shift in the balance of power between the media, governments, and us, the public. So, let's just quickly recap how this telenomacy changed everything. 1. Live news was suddenly faster than official diplomacy. 2. Huge global events became these shared live experiences for all of us. 3. Public opinion, fired up by these images, became a real, direct force in foreign policy. And 4, because of all that, governments had to learn to make huge decisions way, way faster than ever before. You know, if you've ever looked up at the night sky and seen that string of pearls just gliding silently across the stars, you've probably seen Starlink. We all think of it as the future of the internet, right? But its past is rooted in something else entirely. The story behind your internet connection is actually a wild ride through top-secret Cold War history, and that's exactly the story we're going to unpack right now. It's a weird question, isn't it? I mean, on the surface, what's the connection? One is for binge-watching shows,
The other was the super controversial plan for a space-based missile shield. But as we're about to see, they are deeply, and I mean directly, connected. And there it is. The family tree of your broadband internet has a direct ancestor, the Strategic Defense Initiative, or SDI. This was a program that was as ambitious as it was contentious back in the 1980s. So let's jump back in time and see how this absolutely radical idea was born. Okay, so our story kicks off at the absolute height of nuclear tension. The U.S. was desperately searching for a way to defend against a potential missile attack, and the answer they came up with, it was straight out of science fiction. So in 1983, President Reagan proposes SDI. The whole goal was to build this protective shield in space to stop ballistic missiles. The media, of course, nicknamed it Star Wars, and at first, the ideas were pretty wild. We're talking giant laser-wielding battle stations. But that plan pretty quickly evolved into something much, much more sophisticated. And that evolution led to this concept called brilliant pebbles. Get this. Instead of a few massive, crazy expensive battle stations, the new idea was to launch thousands of small, smart, and totally independent interceptor satellites that would just swarm in low Earth orbit, waiting. So how would this crazy space shield actually work? Well, it was designed as this huge dispersed cloud. Each pebble was basically a sensor package attached to what they called a kinetic kill vehicle, which is just a fancy term for a projectile that doesn't explode. It's designed to destroy a missile simply by crashing into it at incredible speed. And by having thousands of them, the whole system would be incredibly resilient. You could take out a few, maybe even 100, but the rest of the swarm would still be up there ready to do the job. Now, what's really mind-blowing here is the autonomy that was required. Because of the incredibly short flight times of these missiles, there was just no time for a human to be in the loop. The system had to detect a launch, the satellites had to talk to each other using laser links to track the target as it screamed across the sky, and then engage, all of it completely on its own. This, of course, presented a massive, massive challenge. You can't build thousands of these things using the old method, carefully hand-building one bespoke spacecraft at a time in a clean room. It's just not possible. You needed an assembly line. This was a totally revolutionary concept for the space industry, a shift from old-world craftsmanship to modern mass production. So, what happened to this radical idea? Well, the Cold War ended, and that immediate threat of nuclear war kind of vanished. But an idea this powerful, it doesn't just disappear. Let's see how it survived. The official program was canceled in the early 90s. And in a way, it was a victim of its own success. With the fall of the Soviet Union, its whole reason for being was gone. But the intellectual capital, the engineering blueprints, the core concept, that survived. And this quote just says it all. Even though the military program was dead, the idea of a massive, communicating constellation of small satellites in low Earth orbit, well, that became the ultimate goal, the holy grail for a whole generation of space engineers. They knew the architecture worked, it needed a new mission. Which, of course, brings us to today. That new mission? It turned out to be providing internet to the entire globe. The military's killer swarm found a completely new life as a communications network. Okay, look at this. The parallels here are they're striking. The engineering DNA is literally identical. Thousands of cheap, mass-produced satellites, check. A mesh network of inter-satellite laser links, check. Autonomous operation in lower Earth orbit, check. The only thing that's changed is the payload, the mission. They just swapped out kinetic interceptors for broadband routers. That's it. And think about this for a second. Those laser links that were absolutely essential for handing off missile tracking data from one satellite to the next, that's the very same technology that now passes your data between satellites at the speed of light in a vacuum, reducing lag for gamers and giving high-frequency traders a millisecond edge. It's wild. And the connection, it's not just conceptual, it's also human. People like Mike Griffin, who worked directly on the Brilliant Pebbles program, they brought their deep, deep understanding of this architecture with them. They were instrumental in the early days of SpaceX, helping to bridge that gap between a Cold War military concept and its new life out in Silicon Valley. Which brings us to the final, and maybe the most fascinating chapter of this story. Because after decades out in the commercial world, this technology is now, in a way, coming home. So SpaceX has now created a dedicated version of Starlink just for government and national security use, and it's called Starshield. It leverages the exact same mass-produced satellite architecture, but it's tailored for missions like secure communications and Earth observation. And this is where the story really comes full circle. Starshield is now effectively providing the U.S. military with that exact same resilient, global, low Earth orbit layer that was first dreamed up for brilliant pebbles way back at the height of nuclear tension. The vision has finally been realized, just decades later and through a completely commercial pathway.
What could possibly connect the glasses sitting on your nightstand with the high-stakes world of missile defense and combat jets? The answer is a single, almost magical metal alloy, and its story is way more fascinating than you'd think.
We've all been there. You sit on them, you drop them, you just toss them in a bag and crunch. The frames are bent completely out of shape, or worse, snapped. It's just a simple, super frustrating everyday problem. Okay, now let's flip that completely on its head. Think about the extreme challenges of combat flight. Imagine these violent, bone-rattling vibrations, the intense heat of re-entry, the freezing cold of space. Here, a single tiny component failing isn't just an annoyance, it's catastrophic. It's game over. These are some of the toughest engineering problems you could possibly imagine. So how on earth do we get from a pair of busted glasses to a high-performance fighter jet? Well, it turns out there's this direct, unbreakable connection between solving that everyday frustration and the incredible materials that were designed for those extreme environments.
So our story kicks off, as so many of these big tech leaps do, smack in the middle of the Cold War. This was an era of just intense competition, right? Scientists and engineers were being pushed to the absolute limit to create materials with properties that just didn't exist in nature, all to get a technological edge.
At the U.S. Naval Ordnance Laboratory, researchers were tackling a very specific, very tough problem. They needed a new kind of metal for the nose cones of missiles, something that could survive the absolute punishment of blasting into space and screaming back through the atmosphere without failing. They needed a real-life supermaterial.
And what they found? Man, it went on a journey that nobody could have possibly predicted. From this accidental discovery back in '59 to being a crucial part of the F-14 Tomcat, then jumping into pioneering medical devices in the '70s and '90s, and finally, believe it or not, landing in the glasses on our faces. It's been quite a ride.
But here's the thing. This wasn't some planned genius breakthrough. Not at all. It was a complete and total accident. Two researchers, William J. Buehler and Frederick Wang, were working with this alloy of nickel and titanium. They bent a strip of it, and then when they applied some heat, it violently snapped right back into its original shape. It was one of those pure aha moments that would totally change material science forever.
So what in the world was going on here? How can a piece of metal remember its shape? Well, this isn't magic. It's all about a really unique and fascinating property of its internal atomic structure. Let's dive into the science of how this actually works. This material, which they cleverly named Nitinol, that's for nickel, titanium, and the Naval Ordnance Laboratory where it was found, is what's known as a shape memory alloy. And the secret to its memory is its amazing ability to switch back and forth between two totally different solid crystal structures. Okay, think of it like the metal has two different personalities, and it's all based on how its atoms are arranged. In its cold state, the atoms are in a formation called martensite. It's soft, it's easy to bend, you can deform it into any new shape you want. But when you heat it up past a certain temperature, its atoms do this little shuffle and rearrange into the austenite phase, which is a strong, rigid structure that is the original shape it remembers. And that atomic shift is what causes it to snap back with such incredible force.
This transformation gives Nitinol two amazing, game-changing properties. The first is that shape memory we just talked about, the whole return to a shape when heated thing. But the second one, superelasticity, is just as mind-blowing. It means the alloy can be severely bent or twisted out of shape, even at room temperature, and it will still just spring right back to its original form with zero permanent damage.
So, you've got this incredible new material. The first big question was, okay, what do you do with it? The answer took it from the battlefield all the way to the operating room.
Its first major job was on the legendary F-14 Tomcat fighter jet. See, they had this problem with hydraulic lines vibrating loose, so engineers came up with this genius solution. They'd take a Nitinol sleeve and cool it way down so it was in its soft, bendy phase. Then they'd expand it and slip it right over the pipe joint. As the sleeve naturally warmed up, it would transform back to its original, smaller, memorized size, shrinking down with immense force to create a perfect, vibration-proof seal. So cool. But the technology's most profound impact, its most important job, was still to come. In the early days of angioplasty, doctors could open up a blocked artery, which was great, but they faced this huge problem called restenosis, where the artery would just collapse or narrow down again after the procedure.
Nitinol's superelasticity provided the perfect solution. Doctors could create a tiny little mesh tube, or stent, out of nitinol, crush it down small enough to fit inside a catheter, guide it all the way to the blocked artery, and then just release it. And once it was deployed, the nitinol stent would automatically spring back to its original expanded shape, creating a permanent scaffold to hold that artery open.
And the impact has just been staggering. Today, millions and millions of people are walking around with these tiny devices inside them. Devices that are direct descendants of a material first designed for missile nose cones, literally holding their arteries open and saving their lives. It's an unbelievable journey for a piece of technology.
And this brings the story full circle. From the most extreme, high-stakes applications you can imagine, right back to that simple, everyday problem we started with.
Yep, in the mid-90s, an eyewear company called Marchand had a light bulb moment. They realized that Nitinol's superelasticity was the perfect fix for the age-old problem of broken glasses. They launched their Flex-On line, frames that you could literally twist, bend, sit on, and they would just snap right back into shape.
And there you have it. That's the incredible journey of this material. Something designed for the brutal rigors of space warfare, found its first real use securing pipes on a fighter jet, went on to revolutionize medicine by saving millions from heart disease, and finally ended up solving the simple problem of our fragile eyeglass frames.
So, carbon fiber. It's everywhere, right? Supercars, fancy bikes, airplanes. It just feels like a material from the future. But what if I told you its real story is a secret? One that wasn't born in some sleek design studio, but in the intense heat of the Cold War. Let's dig in. You've seen it, I'm sure. A Formula One car crashes, and it's just this explosion of parts. Wheels go flying, the bodywork shatters into a million pieces, the car is absolutely obliterated, and then the driver just unbuckles, climbs out, and walks away. How on earth is that possible? Well, the answer isn't just about clever design. It's about the very material the car is made from. And the secret ingredient is a revolutionary composite that, believe it or not, was never meant for a racetrack. Its story really begins with rockets, missiles, and that high-stakes race for the stars. To really understand the impact of this stuff, we have to go to the exact moment it silenced all its critics, right in the middle of the high-speed, high-stakes world of Formula One.
Okay, picture this. The year is 1981. The McLaren team rolls out its brand new MP4/1 car, and it is a massive gamble. Instead of the typical aluminum frame, the core structure, the part that's supposed to protect the driver, is made of something new and totally unproven: carbon fiber composites. And let me tell you, the rest of the racing world was deeply skeptical. They called it black plastic. The common fear was that this stuff would be brittle, that in a high-speed crash, it wouldn't bend or crumple like metal, it would just shatter into a million deadly shards. And then came the ultimate test. At the Italian Grand Prix in Monza, driver John Watson crashes at over 140 miles per hour. The car was torn to shreds, but the most important part, that carbon fiber survival cell, didn't shatter. It stayed perfectly intact, absorbing all that insane energy and saving Watson's life. In one fiery moment, carbon fiber went from a crazy risk to the undisputed future of motorsports.
So, if this material was so mind-blowing in 1981, where did it even come from? For that answer, we need to jump in a time machine and rewind the clock more than 20 years, right to the peak of the space race.
The whole story really kicks off here in 1958 in a Union Carbide lab. A scientist named Dr. Roger Bacon wasn't trying to build a race car at all. He was just doing some basic research on carbon when he stumbled upon something incredible: tiny, perfect filaments of carbon that were unbelievably strong, yet weighed almost nothing. He called them graphite whiskers.
So what problem were they trying to solve with this stuff? Well, the military had a huge one. The exhaust blasting out of a solid rocket motor was so hot it could melt tungsten, and that's one of the toughest metals we have. They needed something even more resilient.
Dr. Bacon's discovery was the key:
By mixing these carbon fibers into a carbon matrix, they created a composite that could survive those insane temperatures through a really cool process called ablation. Instead of melting down, the material just slowly and controllably erodes, layer by layer, carrying that destructive heat away with it.
And you've got to understand how vital this secret material became. We're talking about the nozzles for nuclear deterrence like the Minuteman and Polaris missiles. It was the stuff that formed the nose cone and the leading edges of the space shuttle's wings, protecting the astronauts from the searing heat of re-entry. This was top-of-the-line, classified technology.
So how does a top-secret missile component find its way into our golf bags and tennis rackets? Well, that transformation happened because of a pivotal and kind of surprising international deal.
The crucial turning point was in 1970. Union Carbide, the American defense contractor, signed a technology exchange agreement with a Japanese company, Toray Industries. This deal was huge. It basically unlocked carbon fiber from its military-only cage and opened the door for it to be used by everyone.
And Toray's strategy was just brilliant. First, they perfected a way to mass-produce these fibers using a synthetic polymer called PAN as a starting point, which made it cheaper and more consistent. But their marketing move was genius. Instead of trying to sell it to huge industrial companies, they targeted sporting goods manufacturers, who they knew were desperate for any competitive edge.
This timeline really lays it all out, doesn't it? It starts with that quiet lab discovery in '58. Then you have the critical tech exchange in 1970 that just blew its potential wide open. Just 2 years later, it's in golf clubs and fishing rods. And all of that culminates in that spectacular, very public validation on the racetrack in 1981.
Let's just zoom in on one specific example to see how incredibly disruptive this new material really was. Let's talk about tennis.
Before carbon fiber, tennis rackets were made of wood. They were heavy, they have these tiny little heads, and you needed incredible precision to hit the ball well. The arrival of carbon fiber changed literally everything. All of a sudden, rackets were lighter, stronger, and could be designed with much, much larger heads.
So, why could the heads get so much bigger? It all comes down to one key property: stiffness. If you tried to make a big racket head out of wood, it would just warp and lose its shape. But carbon fiber's incredible stiffness-to-weight ratio meant designers could create these huge sweet spots without the racket becoming unstable or too heavy to swing.
And the result wasn't just a new piece of gear. It was a whole new way to play the sport. The delicate touch-based style from the wood racket era gave way to the power baseline game we see today, where players can generate incredible speed and spin from way back in the court. So, from missile nozzles to tennis rackets to Formula One cars, the journey of this material was already incredible. But it was all leading back to the industry where the dream began in the first place: aerospace.
I mean, this journey is just fascinating when you break it down like this. It had to be born in secret to solve an extreme military problem. Then, it had to be tested and perfected out in the open in the super competitive world of sports. All of that development, all those lessons learned, finally made it strong enough, light enough, and affordable enough for its ultimate destiny.
And this is the culmination of it all, the Boeing 787 Dreamliner. It's the first major airliner where the main fuselage and wings aren't made of aluminum, but of carbon fiber reinforced plastics. This fulfilled the original dream of the aerospace industry, a material strong enough for flight, but so light that it creates massive gains in fuel efficiency.
What on earth could possibly connect the soft mattress you sleep on with the tough lenses protecting your eyes? I mean, they seem like they come from completely different worlds. And, in a way, they do. Just a world that's about 238,000 miles away from our own. And the answer, incredibly, is the Apollo space program. Yep, that monumental push to put a human on the moon forced science and engineering to its absolute limits. And the amazing solutions they came up with, they didn't just stay in space, they found their way back down to Earth in some really unexpected ways. So, let's start with how they solved one of the most violent parts of any space mission. Our first story begins not with a gentle landing, but with one of the most intense moments an astronaut has to go through: coming home. This is the story of memory foam. Okay, so picture this. An Apollo command module is hurtling back through the atmosphere, and then it splashes down hard in the ocean. The astronauts inside are slammed with these immense gravitational forces. We call them G-forces. So NASA had this critical challenge. How in the world do you cushion a human body to survive that kind of brutal impact? Well, back in 1966, NASA tasked an engineer named Charles Yost with inventing a solution.
And what he came up with was this remarkable material called viscoelastic foam. The genius of it was its strange, kind of dual nature. When you put pressure on it, it would flow like a thick liquid, molding perfectly to any shape. But as soon as you took that pressure away, it would spring right back to its original form, just like a solid.
This stuff, which they nicknamed temper foam, was the perfect fix. They lined the astronauts' seats with it, so when that capsule hit the water, the foam would just soak up that massive shock of impact. But here's the crucial part. It spread those G-forces evenly across the astronaut's entire body, which almost certainly prevented what could have been some really catastrophic injuries. But this amazing material didn't just magically show up in our bedrooms. For years, the manufacturing process was just incredibly complex and way too expensive. The real turning point came in the 1980s, when NASA, as part of its mission, released the formula to the public. And that's when a Swedish company finally figured out how to mass produce it, which led to the very first Tempur-Pedic mattress hitting the market in 1991. And today, its impact is just huge. The exact same technology that protected astronauts during a violent splashdown is now used in hospitals to prevent painful bed sores for patients. And of course, it gives millions of us a really comfortable night's sleep. So that's how NASA protected an astronaut's body. But what about one of their most critical instruments, their vision? This brings us to our second invention, which also started with a life or death problem in the incredibly harsh environment of space. You have to understand, the environment outside of a spacecraft is just unbelievably harsh. You've got the blinding, unfiltered glare of the sun. You've got dust and tiny micrometeoroids zipping around at incredible speeds. A single deep scratch on a helmet visor could totally distort an astronaut's vision during a critical moment, or even worse, compromise the integrity of the whole helmet. NASA needed a visor that was both perfectly clear and incredibly tough. The solution came from their Ames Research Center, a special, transparent coating that could be applied right onto the plastic visors they were already using. And the difference was, well, night and day. Compared to standard plastic, which, scratches if you just look at it wrong, NASA's new diamond-like carbon coating was a total game changer. It was perfectly clear to see through, but it had the surface hardness of glass, making it incredibly durable. So how much more durable are we talking? 10 times. This coating made plastic visors 10 times more scratch-resistant than the regular plastic they used before. That's not just a small improvement. That's a massive leap forward in safety. And just like our story with memory foam, this tech didn't stay locked up in space. In 1983, the eyewear company Foster Grant licensed the patent from NASA. It was a perfect textbook example of a direct technology transfer, taking the exact science designed for the moon and applying it to our everyday sunglasses. So what's the big picture here? What does this all mean? Well, these two examples are part of a much bigger story about how the sheer ambition of space exploration creates real, tangible benefits for all of us right here on Earth. You can see the pattern so clearly when you lay it out like this. In both cases, there was an extreme problem that was pretty much unique to space travel. That problem forced a brilliant and very specific solution. And that solution, once the core technology was perfected, turned out to be versatile enough to solve a completely different set of problems for all of us back on Earth. This incredible pipeline, this journey from a space-age problem to a household solution, actually has a name. It's called technology transfer. It's the official process of taking these inventions that were created for the unique challenges of space and adapting them for commercial and public use.
It's a huge question, right? You hear about climate change constantly, but when you boil it all down, what's the actual hard evidence? Well, a massive piece of that puzzle is found in a place most of us will never, ever see, the Arctic.
For more than 40 years now, scientists have had this incredible, unbroken stream of data that tracks the sea ice in the Arctic. Think about that, an uninterrupted record. It's basically a priceless scientific baseline that lets us see long-term changes with really unbelievable clarity.
And let me be clear, this dataset is an absolute cornerstone of modern climate science. It is the primary, smoking gun evidence that shows us just how fast the Arctic is changing. It's one of the most powerful signs we have of a warming planet.
Okay, but here's the twist. What if I told you that this crucial scientific tool wasn't born in a university lab or some civilian science agency? What if its real origin story is all about espionage, Cold War paranoia, and a military program so secret that for years, its very existence was denied.
To get this story, we have to go back in time. We're not starting with climate scientists, we're starting with Cold War spies. The US was desperate to get a look inside the Soviet Union, but they kept running into this one really annoying, unexpected problem.
That's right, clouds. You have to remember, the very first spy satellites, the Corona program, they were literally using film, actual canisters of film that they dropped from orbit to be caught by a plane. You couldn't afford to waste a single shot on a bunch of clouds. So the military had an urgent problem. They needed a rock-solid weather forecast for the skies over the USSR.
Now, you've probably heard of NASA's TIROS program from 1960. It was the public face of weather satellites, totally groundbreaking stuff. But behind the scenes, in the shadows, the military needed something way better, way faster, and, most importantly, totally secret. And so, they created the DMSP, the Defense Meteorological Satellite Program. This thing was a black program, completely off the books, designed to give them a tactical edge.
But this is where the story takes a much darker turn. Because once the military got really good at predicting the weather, somebody was bound to start asking, well, what if we could control it?
And just like that, they went right down the rabbit hole of weather modification, the idea that you could actually intentionally change the weather to achieve a military goal. And during the Vietnam War, this wasn't some sci-fi theory. It became a classified reality.
This was the motto. It's chillingly simple. The top secret mission was called Operation Popeye, and the goal had nothing to do with winning firefights. The goal was to weaponize the monsoon season itself and grind the enemy's supply chain to a muddy, impassable halt.
So, how'd they pull it off? Well, using all their fancy new weather data, they'd pinpoint the perfect cloud formations over the Ho Chi Minh Trail. Then, they'd fly these seeding missions, dumping silver iodide into the clouds to trigger massive downpours. The whole point was to artificially make the monsoon season longer, washing out roads, causing landslides, basically making it impossible to move troops and supplies.
This program ran in total secret for 5 years. They flew over 2,600 missions. But in 1971, a journalist named Jack Anderson got a tip, and he blew the whole thing wide open. The public outcry was huge, and the international scandal eventually led to a major treaty in 1977 that straight up banned using weather as a weapon of war.
Now, you'd think that's where the story of the DMSP satellites ends, right? A secret program, a scandal, a treaty, but you'd be wrong. Because what came next was this totally remarkable accidental gift to the world of science.
Starting in 1972, and then a much bigger dump in 1994, this massive archive of data from these secret spy satellites was declassified. All of a sudden, civilian scientists got their hands on decades of detailed, global environmental information they never even knew existed. I mean, it was an absolute gold mine.
And the tools on these satellites were amazing. Take the OLS sensor. Its military job was to be so sensitive it could actually see clouds just by the light of the moon for nighttime operations. But it turned out it could also see city lights, and pretty soon economists realized, whoa, we can use this to track economic growth and GDP from space, especially in places where official data is, a little sketchy.
And then there was the other key piece of tech, the SSMI sensor. This thing could see right through clouds and polar darkness using microwaves. Its military mission? To help nuclear submarines find gaps and openings in the Arctic sea ice. But for scientists, this was the holy grail. It was the key that unlocked our ability to track sea ice all year round, leading directly to that priceless 40-plus year climate record we talked about at the very beginning.
It's just an incredible arc when you think about it. A technology built for war, for espionage, for secrecy, completely transformed into a tool for global understanding. This secret program left behind a legacy that absolutely no one could have ever predicted. And this quote from our source material really just says it all perfectly. The very sensors designed to help nuclear subs navigate the Arctic, they're now the sentinels, the watchtowers, that are warning all of humanity about a warming planet. It's just a profound and absolutely unexpected transformation.
And this is the iconic image, isn't it? The one that defines our whole era in space. A rocket booster literally taller than a 14-story building, riding a pillar of fire back down from the heavens to land with pinpoint accuracy. It just feels so brand new, doesn't it? The ultimate symbol of 21st century innovation. But is it really?
And this is where we get to the heart of the mystery. See, there are two stories here.
The one we all know is about private sector genius, Silicon Valley-style innovation, completely disrupting a slow, old industry. But then there's this other story, a hidden history, a story about a technological ghost that basically laid the groundwork for everything we're seeing today.
Well, that ghost has a name, and it's time we talk about it. Let's dive into the story of a forgotten prototype called the DCX.
So here's the first thing you have to understand. This was not a NASA science mission. No way. The Delta Clipper was a pure military project. It came straight out of the Strategic Defense Initiative. You probably know it by its famous nickname, the Star Wars program. And its whole job was to be a cheap, reusable launcher. Think of it like a space truck. Its mission? To launch this massive constellation of military satellites. And believe me, it looked and flew like absolutely nothing else out there at the time.
And the progress they made was just staggering. In just a couple of years, the DCX basically proved the impossible was possible. It took off, it hovered in midair, it moved sideways, and then it landed vertically. All the key maneuvers we see today. It even flew twice in a single day, proving that rapid reusability wasn't just a fantasy. But its life was cut tragically short. It got handed over to NASA, and on one of its flights, a single landing leg failed to deploy. That's it. The whole vehicle just tipped over, and the entire program, all that promise, just went up in smoke.
And all of this happened because of the program's totally radical mindset. You have to remember, traditional aerospace was super slow, super risk-averse. But the DCX team, they had this fail-fast, fly-often philosophy. They ran the whole thing with a tiny crew, and their goal was to learn from mistakes as fast as possible, not to try and avoid them at all costs. I mean, come on, that's literally Silicon Valley culture, decades before SpaceX made it famous.
So yeah, the rocket was destroyed, the government funding dried up, and that was that. Or was it? Because the hardware might have been gone, but the data, the engineering knowledge, and crucially, the proof that vertical landing actually worked, all of that survived.
So the big question is, how did all that knowledge from a dead military project end up at the absolute heart of the commercial space revolution? Well, let's trace the technological DNA.
Okay, first you gotta understand the signature move of a Falcon 9 landing. It's called the suicide burn, and yeah, it is exactly as dramatic as it sounds. The rocket is literally plummeting towards the Earth, and then at the absolute last possible second, it fires its engine to just slam on the brakes and touch down. It is an unbelievably complex and risky maneuver.
And the software that makes that possible, that incredibly complex stream of data and commands, the basic control logic that lets them pull off that heart-stopping move, well, it wasn't invented from scratch in the 2010s. It is a direct evolution of the work that was pioneered by
The forgotten Delta Clipper. Yep, that's the connection. That's the ghost in the machine. The core software and control logic that lets a Falcon 9 land today, its DNA comes directly from that project in the 90s.
I mean, you can trace the flow of this knowledge almost perfectly. Step 1. It all starts with a military need for a cheap, reusable launcher. Step 2. A test vehicle, the DCX, proves the whole concept is possible. Step 3. The government's interest fades and they cancel the program. But, and this is the key part, the engineers and all that priceless data, they don't just vanish. They migrate over to the private sector, to ambitious new companies like SpaceX and Blue Origin. And those companies take that foundational knowledge and build a multi-billion-dollar industry on top of it.
Look, the story of the DCX isn't some weird one-off thing. It's actually a perfect example of a powerful historical pattern that repeats over and over and over again. And this is where the story comes full circle. It's beautifully ironic, really. The DCX was first created to launch a military satellite constellation called Brilliant Pebbles. Okay, that project died on the vine. But the technology it pioneered is what ultimately enabled a private company, SpaceX, to launch its own massive constellation, Starlink. And what is Starlink today? Well, among other things, it's become a vital strategic asset for militaries around the world. So in a way, the original mission was actually fulfilled, just not at all in the way anyone expected.
In this pattern, this transmutation of military tech into essential civilian tech, it is literally everywhere you look. Those old Cold War command and control satellites, they became the GPS that's in your phone right now. The systems built to detect nuclear tests, they laid the groundwork for what became the internet. So when we look at the cutting-edge defense projects of today, things like hypersonics and nuclear thermal propulsion, you just have to wonder, what civilian miracles will they turn into tomorrow?
And that really brings us to the core lesson here, doesn't it? The takeaway is that we have to recognize this dual-use nature of technology from the very beginning. The challenge isn't about stopping military innovation, not at all. It's about figuring out how to build bridges, how to create pathways for these incredibly powerful, often taxpayer-funded ideas to move from the closed-off world of defense into the open, where they can actually benefit everyone.
So, that leaves us with one final and I think really important question. When we look at all the advanced, even classified research that's happening right now, what future miracles are being born? What technologies are being invented today that will one day cure diseases, or connect our world in new ways, or maybe even open up the entire solar system for us in ways we just can't imagine yet? The ghost of the DCX is a powerful reminder that they're out there, just waiting for their moment.